So now I'm coming to the second half of the first part. So that's about what happens if we add the notion of distance. So in the previous presentation I didn't mention that there are some distances between points, and now we just expect that our surface, so say let's take it again as the desk of ours, so that's the surface of the table, and imagine that we know what the distances are. We have got some ruler and we can measure how far the points are, and it will be seen that it's roughly speaking again the same as choosing some reasonable basis vectors. So in our coordinates it means that we not only take the origin 0 or O, but we declare that the first vector E1 and the second vector E2 will be what we call perpendicular. E1 perpendicular to E2. And well, by some engineering approach, why not? We know what it means in practice. But mathematically speaking, we could just declare about any two vectors which are not collinear that they are for us the perpendicular ones, because that exactly happens if you just see something in perspective as I was drawing it, right? So in the picture they are actually not perpendicular. So it's just our choice which two vectors we declare to be perpendicular and of size 1. So the magnitude of the vectors is declared to be 1. And this defines for us the distance. And then we know that for each vector, say v, which has got the coordinates x and y in our coordinate system, the square of the size of v is simply x squared plus y squared. That's what we simply know from the Euclidean theorem, right? So here is the right angle, here is x, here is y. So x squared plus y squared is just this one. And we know that this could be also seen from our understanding what means area and volume, etc. So we shall come to that. So, and related to that, of course, there is a question then, what are the transformations which keep the size, and with the size there are also the angles, right? So this is something like an angle. So this will be for me angle phi. So we are wanting to know what the rotations will be. And that's not something very complicated, because we of course can define some function to measure it for us, and that's what is usually done in such a way that you take the unit sphere. So here is the E1, here is the E2, this is the unit sphere, and we simply say that this is phi, and this value will be sine of phi, while this value will be cosine of phi, right? And that's the definition of the function, just how big this x coordinate of the given point P is. That's the cosine of phi, and this is the sine of phi. And now, of course, the rotation by the angle phi is easy to write down, because we know that it will be just what we have got here, so I don't have to draw it again. So we want to know what the A, B, C and D would be, what they would be, right? So I want to make this, and it doesn't want to work with me, I don't know why. This way, yeah, I have to hit it twice. So we want to know what the 4 unknown scalars are, and we know that we are rotating by the angle phi. So that means that the first column of the matrix, the A and C, will be given by depicting it on 1 and 0, and we see what happens, right? So this will be cosine, well, I call the angle psi here, cosine psi, and The other coordinate is sine psi. That's just what's there. And then I do the same with 0, 1. So I want to look at this point and tell where it goes. And it's easy to see that it will be exactly these two. So this is the matrix of rotation, right? So it's easy to see what to do in the matrix calculus. And now the nice thing is that if we want to compute the angle giving two vectors, so if we take this vector and this vector, then we see that actually the cosine is given by the scalar product of the two vectors. And that's because the vectors have got magnitude 1, so the size is 1. And in general, the angle shouldn't depend on the size of the vectors, so we have to normalize them. And that's obtained by taking the right formula, and that was the formula which I skipped here. So this is the formula for the cosine, right? So you take the scalar product of the two vectors who are normalized. So that's a very important thing, and there is the definition and there is the argumentation in the text so why this works in any coordinates. So any coordinates which would just give you the same sizes, and we shall see immediately also in the text which one are they, it works. And then what I look at is what happens if I want to rotate in the plane, but say the center of the rotation should not be the origin. So we found the matrix of the rotation around the origin. So, but that's easy because we can just go for our affine mappings, first shift the given center to the origin, then make the rotation, and then to shift it back. And that's extremely easy. So that's what you get. Where is it? Here. So that's the composition. That's the rotation composed with a shift, right? So we first shift to 0, then we rotate, then we shift back, and the result is what we get. So you see, the matrix calculus makes all the things in the plane computer graphics extremely easy. The next thing which is discussed here is the reflections. So the reflections are very easy going. So the easiest one is the reflection with respect to the x-axis. So that means just that if you reflect with respect to the x-axis, so this is the picture then. So these are the two axes. I simply want to reflect. So the x-axis keeps going, and the epsilon coordinate simply changes the sign. And that's exactly what happens with this matrix, right? No problem to see that, I guess. You just keep the x coordinate and change the sign with the y coordinate. And if you want to make the same with respect to another line through the origin, then you simply first rotate the line to the x-axis, then you perform the reflection we know about, and then you come back by rotating again. And that's again via the matrix calculus, absolutely easy. So that's nice. And here we see that's the explicit computation that if you do two reflections one after the other with respect to lines through the origin or through the same point, which have got the angle phi between of them, then it's the same as rotating by, well, as you see here. So that's where is it? Here, a rotation through angle psi can be obtained by two subsequent reflections, where the angle between the lines should be half of the angle of the rotation, right? So if you do two reflections, you get actually always a rotation if the reflections are and the rotation will be through the center, which is the intersection of the two lines. So that's again a very useful thing, and you can enjoy looking at the proof because either you believe in synthetic geometry and the proof from the picture, which is very concise and okay, and then what you get out of that is the well-known rules for the computations with double angles for the function sine and cosine, or you know this from your secondary school, and then you don't need a picture and you can just use it straightforwardly in an absolutely algebraic way via the matrix calculus, right? So you can go one or the other way, and then either the matrix calculus proves this equations one, or you use the equations one and prove the result, right? So that's something I really like to see. Right, the last thing I want to talk about here is what are the areas. So we want to first of all just declare for simplicity that we are modest and we would be happy to know what are the areas of triangles. But the areas of triangles are pretty easy to guess, because you see on the picture that actually you can make twice the thing of the triangle, so this parallelogram, into a, well, not square but rectangle of the same area, right? So simply this part is the same as this part, so it works. And then it's clear that what we want to see is that the area of the triangle will be 1/2 of the size of one of the vectors and times the size of the height. So the height of the triangle is what we want to see. So that's this one, right? Right, that's an understandable formula, and in particular you see immediately from the picture that it's a very nice formula, right? So that means that it will be definitely linear in both v and w, because if you multiply v, you clearly the same way multiply the size, and the same with the w, because the height behaves this way as well. So it's just on this picture, right? So linearity in the argument. And now you can imagine that you prefer to distinguish the order how you define the triangle. So whether if you take the vertex, whether you, so I may better to draw it. So you would have one of the possibility, this is just the first vector, say v1, and this is the second vector, v2, right? And you would then see this area in a positive way. So you imagine you view it from above, say, right? So that's the positive orientation. And you want to distinguish it from the possibility that you view it from the other side, which would be just if the v2 was the first one and v1 was the second one. And then you take the same area but with other sign. So the area would be equipped with a sign. But then it's a linear thing in both of the arguments, which has the property that if you swap the arguments, you change the sign. And that's what we call the antisymmetric bilinear form, right? Something which is, it's clear, it's linear in each of the arguments, therefore I call it bilinear. It's a form because it's something which is linear in the arguments and valued in scalars. And it's antisymmetric because if I change the order of the arguments, it changes the sign. Right, but now, because we know that it's bilinear, so it's enough to evaluate it on the basis vectors, right? Because all others are linear combinations of those. So everything else can be then computed from the values. And if we are in 2 dimensions and we have got 2 arguments, then the only thing you can plug in is both of the arguments, right? Because if we would put there twice the same one, then the rule about swapping and changing the sign would mean that it's 0, right? So it's not interesting. So you see that up to multiple, there is only one antisymmetric bilinear form. And just browsing back a few pages in the notes, I could show you that the determinant has got this property. And the determinant of a matrix, so if I write a matrix, that was not the right one. If I write a matrix A, B, C, D, then the determinant was A times D minus B times C. And if I would think that this is the first vector and this is the second vector defining my triangle, then if it was the unit circle definition triangle, then there would be a unit matrix. Right? And it would be 1, 0 and 0, 1. And we know that the area of the unit square should be 1, and so the determinant is the tool computing the area. And then this is used in computer graphics in a very fancy way or easy way, because you can easily decide whether your point C is on the left or on the right of the directed line. So I take the A and B and mean AB as defining an oriented line or segment, and the question is whether C is on the left or on the right. And that's the same thing as discussed visibility, and you can see it easily by computing the area via the determinant, and you just adopt the convention that from one side you see the segment, and that would correspond, say, to positive determinants, and from one side you don't. And that's exactly what's used for visibility, right? So let me end with this. Right, I will explain later what the shears are and come back to some practical illustration in another video soon, right? So let's stick with what we've seen, and thank you again for the second part of your attention this week.